Yeah, it's actually very nice eventually to speak here and present some of the work, some of the results that have accumulated over the past 26 years that I have been at Erlangen. You see here that my affiliation, Erlangen, is still my affiliation. I will go into retirement end of March. I used to be the team leader at Surfax for the algo team, parallel algorithms team. I've also stepped down by the end of last year, but that's still there as an affiliation because some of the work is also with collaboration from there. And then I'm more recently a little bit affiliated with the Technical University of Ostrava, where I've actually been last week for another conference. And so this is kind of the outlook also, what I'll be doing after retirement, a little bit here, a little bit there, and so on. So my work has centered around efficient solvers for partial differential equations, in particular also very high performance computers. And a good deal of the audience that's present here, and some also remotely, happen to be my PhD students. And I should take reference to that in two different ways. First off, the work that I'm presenting is, of course, to a very good deal, essentially all of it, based on what the PhD students have been doing over the last years. And that's very good that they are here. So if there are any detailed questions, the experts are partly sitting here and can then help me to answer any questions. And on the other hand, an apology to the PhD students, because of course a good deal of what I'll be showing is known to you. So I hope that you're not too bored in what's going to happen in the next 45 to 60 minutes. I would like to start with some preamble, and this is exactly what my PhD students know what's now coming. My question to the audience here is, what is the fastest Poisson solver? So the Poisson equation is ubiquitous in many scientific applications. So what is the algorithm that you would say is the fastest one for this problem? And the context, of course, is that scientific computing is about efficient methods. And there's always a trade-off between accuracy and cost. So there's nothing for free. If your accuracy is irrelevant, cheap algorithms are trivial to find. Just take ChatGPT, ask it what is the solution of the Poisson equation. It will say 5. It's very fast and wrong. But if the cost is irrelevant, also the accuracy is trivial to achieve because you just take an infinitely fine mesh and don't worry what it costs. Use just Gaussian elimination as it comes, and no problem at all. So the real problem is to find the right compromise. And that means understanding that trade-off. To understand that trade-off, we need metrics for the cost. And there is this notion of algorithmic complexity and of accuracy, which is the magnitude of the error. That's easily said, but once you start thinking about it, both are surprisingly unclear. So cost could be that you count just the number of unknowns. This is also a cost metric, probably not a very good one. You could count the number of floating point operations that it takes you to deliver a solution. But then, of course, there's also memory consumption and issues of memory traffic that could be the dominating cost factor. You could try to measure runtime, but that's always subject to the computer that you're using. If we had normalized Poisson solvers on a machine from 1970, nobody would have that machine anymore to try out how fast the solvers are. And energy consumption starts to become of concern. And you can cook up many other issues that are relevant to that. With accuracy, at first glance, it looks easier because mathematicians, define all kinds of norms to measure accuracy. But then when you ask individual mathematicians what is the right norm for the Poisson equation, they will immediately come up with 3 different answers. And again, you don't know which is the best one, which is the relevant norm. And then additionally, often it's not the solution that is needed, but the functional bearer of the solution just at a point or some integral over it or something. And that also could make a change of what you really want to compute accurately. Just to mention it, I thought of putting more on it, but then didn't do it. But I would at least like to mention it. Of course, there are people that nowadays saying, use deep learning for solving PDEs. That's the future. So if your natural intelligence isn't enough to deal with numerical PDEs, you can use artificial intelligence. That's one of the steps of progress. So to get deeper into that, I would like to make the question somewhat more clear. What I mean with the fastest Poisson solver? I would like to have something like what we are used to teach students in numerical analysis classes. We tell them that Gaussian elimination costs 2/3 n-cubed flops. And that has two things. It has the exponent of the complexity metric, and it has a dominating factor there. And both are relevant because in numerical analysis, we typically discuss then that if the system is symmetric positive definite, we can use Cholesky, and it has 1/3 n-cubed flops, and is therefore typically expected to be twice as fast. And so you need to both of these things. For PDE, if anybody of you knows something like this for PDE, let me know. I don't. And one of the reasons is, of course, that PDEs are complicated beasts, so we probably have to say more precisely what you want. So let's really focus on Poisson's equation. Let's even go to and say it's the 5-point discretization of the Laplace operator, the simplest one that you have in 2D. That means we are taking away the discussion of accuracy. We just say this is the way how we discretize. And let's also fix for the moment the complexity metric as flops, well knowing that this is maybe not the final thing that we want, but at least that. And so again, the now very concrete question is, what is the costs of solving the discretized Poisson equation on a grid with capital N, meaning little n squared unknowns on the grid with n by n? And if anybody of you has the answer, and my students have to be silent because they know the answer, let me know. And it's surprising that even people that work a lot on numerical PDE would hesitating. They're saying, the best algorithm could be linear and the log term because FFTs can be used and things like that. That is all true, but if you're asking for the constant, hardly everybody can cite that directly. And I insist on the constant because that is when you have the exponent is the same, and in particular when the exponent is close to being linear, then it's actually only the constant that's relevant. All the rest is not important. And this is what you can think about. So let's take the model problem again. Now I would like to also say the right-hand side is smooth, and I would even now spend some 5 minutes to go even simpler for 1D because I want to illustrate on 1D something, and take the boundary conditions simple. So in some sense that we are looking now at the fruit fly for studying PDE solvers. It is kind of the basic example on which you can try algorithms. Is it also of practical relevance? In most cases, you need to generalize it somehow because the domain is not the unit square and the boundary conditions are more complicated and you may have variable coefficients in there. But even that very simple problem is, I think, relevant for some of the applications as it is. But the most important feature of it, that it requires a global data exchange. So though the discretization matrix is sparse, the inverse, if you were to compute it, is a dense matrix. And that means every component of the right-hand side vector influences any component of the result vector. And that immediately tells you that there is somehow a problem of data communication. Say, a neural network that does not have a full connection between the neurons will not be able to do it. Right? If there is no data path from every point of input to every point of output, somehow you will not be able to get a solution. So, and one of the ways how to illustrate is that we really look in 1D for the moment, because in 1D, we can take the ordinary differential equation, second order, right-hand side. We will take actually the right-hand side in many cases 0. And here I've made it such that it has on one side a Neumann condition and the other side a Dirichlet condition. We can quickly look at the eigenfunctions of that. They all have that Neumann condition here and the boundary condition there, and then more and more wiggles in between. So very standard. Many people have seen that in some point. Then we discretize. Here we are now in 1D. So we are getting just a tri-diagonal matrix of that structure. I've left in the matrix away the 1 over h squared factor that would come out of the finite differences, but the tri-diagonal structure is there. It's diagonally dominant, weakly diagonally dominant in almost all rows, except the very last one. And then those who know the theorem of Gershgorin know now that the matrix has eigenvalues bounded away from 0, and that means it is positive definite. Okay, the Neumann condition is these two coefficient entries of the matrix, and the Dirichlet condition are these two conditions in the matrix. And the Dirichlet condition is necessary to move the system away from indefiniteness to being definite. Okay, so what solutions algorithms are there? So to say clearly, the way to solve that is a tri-diagonal direct solver. And since it's symmetric positive definite, it should likely be Cholesky. And interestingly enough, the Laplacian in 1D is a product of div and grad. And if you do Cholesky on the system as I've shown it, it actually recovers as the two factors div and grad discretizations. So that's also nice to know. If you do that on the tri-diagonal system, you get order n complexity. However, you have a sequentiality, both in the factorization, because you have to do it row by row, and also in the forward-backward substitutions that you have to do on the two factors. So you have a very sequential algorithm. And the way to get out of that is to use cyclic reduction as the elimination order. But here we want to study iterative solvers, because in higher dimensions, we want to use iterative solvers. Very clearly, in 1D, don't use the iterative solver because it's not an efficient method. But just to study how it behaves, we look at the 1D problem. So here is how the problem is being set up. And this is the Gauss-Seidel algorithm, not looking at efficiency neither in the coding. The algorithm is not efficient. The coding is not efficient. But for the purposes what I wanted to show, it will be good. And also keep in mind the SOR. Here you have this update rule that UI is updated by 1 over diagonal entries times residual. And if we were putting in an over-relaxation factor, we would get the SOR method here. We'll try both of them. And this sets the problem. I'm now setting the problem that the Dirichlet condition is at 1, and the right-hand side is otherwise 0, set to zeros. And then the exact solution, which I just by brute force, calling up the Python internal Gauss elimination, is this one, right? So it is constant 1. This is the Dirichlet point that determines that. This is U double prime equals 0, and this is the Neumann condition that U prime equals 0 there. So this 1 here from that boundary influences the whole solution all over the domain. And why is that an interesting test case to study that? Because if you now look what happens when we do an iteration like Gauss-Seidel on that. This is one step of Gauss-Seidel. The Gauss-Seidel traverses, sets every point at the average of its neighbors, and that gives averages of 0 all the time, except here where it is the average of a 1 and a 0, and that 1 point has moved, right, to be 0.5. If you do 2 steps of Gauss-Seidel, it looks like that. And the next thing is 5 steps of Gauss-Seidel, and now 5 points have moved. This one, this one, this one, this one, this one, and I think also that one. And in each step, the information from the Dirichlet point propagates by 1 mesh point towards the interior. If you do that more systematically, a slightly bigger grid with 16 points plus the boundaries, I guess we shouldn't worry time-wise about how it is implemented, but I just show you this. So this is the Gauss-Seidel with 1 step, this orange-like color, this one, and then constant 0. This is with 3 steps, so the green points, this curve. And then I'm always essentially doubling the number of steps. So this is steps meaning iterations. This is after 7 iterations of Gauss-Seidel. This is after 15 iterations of Gauss-Seidel. This one, the blue curve. And you see, actually everything should have moved up to here, but it's additional having slowness. So it is even slower than you would expect. And even after 31 iterations, it only looks like this curve here. The point has only moved up to here. And if I again double the cast to 63 iterations, it is this here. And if I double again to 127, it is, I guess, this one. And even if only when I go up to 255, which would be this one, and 511, it's this one. So 511 is still not perfect, as you still see a difference here. But what is actually the really worrying thing is that when you see this one and you have done 255 iterations, it looks like you're 90% there and only 10% of the work is left, but that's not true. Actually, more than half of the work is still left to do, right? So, and this is what one needs to keep in mind for that. So this additional slowness is typical for these iteration methods. And that has to do, if you do that mathematically, quantitatively, you know that the number of iterations is as large as the order of the condition number, and the condition number goes with number of mesh points squared. That means you need at least, when you have 16 points, 255 times the constant, so approximately 4 times 255 is enough to get a reasonable solution. In iteration, and each iteration has always to traverse the whole grid. That's the issue. Therefore, if you did that, you would have a complexity that's cubic in the number of unknowns. How can this be improved? Well, if you have been watching awake, you would say, well, why did you run the Gauss-Seidel method from left to right? When the data is on the right, you should run it the opposite order of the loops. Yep, that helps a little bit, but not in the long asymptotic tail. So it saves you some 10 or so iterations, maybe 50 or so, but not in the hundreds. So more successful to speed it up is over-relaxation or conjugate gradients, because they can in principle improve the number of iterations to order the square root of the condition number. And this is what I can demonstrate here. This is a picture for SOR. I guess I should now show here. The over-relaxation parameter is 1.7. Maybe it is worth to look here. So the first thing, right, if you use Gauss-Seidel, this curve here with the orange points, where the second point is already is still at 0, and only the first point here has moved, has not moved to the middle, but it has been 70% more than where it would naturally go, and that means it's up here. So it's over-relaxation with a 0.7. And if you do this now with 3 iterations, you get this one. If you do it with 7 iterations, you get this one. If you do it with 15 iterations, it goes like this one. The 16th is still nailed at 0 because no information has propagated there. And if you're at 63, it looks like this one. And from about 100 onward, it starts overlapping with the true solution. So that is good, obviously. We see a significant speed up. And of course, we can now systematically study what the best over-relaxation parameters are. That could be done experimentally or analytically. For practical purposes, there is no reason to go to deep analysis, because experiment-wise, you will find quickly what good over-relaxation parameters are. The other competitor that I would like to demonstrate is, what does CG do? And that is maybe something that I would like to challenge you. There are, of course, many people who work on PDEs that use CG. So what would CG, for this example, do differently from the other methods? Try to get a picture in your mind. And this is a CG routine. I stole that from the internet. And also, let's not worry about the driver, but look at the result. So the very first result, just one CG step, delivers the same thing as the Gauss-Seidel. But then this second step delivers this one. After 4 steps, it looks like this one. After 8 steps, it looks like this one. And after 16 steps, it looks like this one. Why is that the case? Well, one way to understand what CG is doing is it takes a linear combination of previous iteratives, and under the linear combination, it tries to find the best possible one. So when you have 2 vectors that have something different from 0 and the 2 rightmost points, it will find the linear combination of them, which is the best possible solution to the PDE. And if you have 7 points that have changed away from 0, it will do a linear combination of these 7 that have different values from 0 here, and it does a linear combination that does the best possible here. Still, so this is a big improvement, of course. And from 16 onwards, because then all points have changed, it will find our linear combination. So the Krylov space is big enough so that you can perfectly represent the solution up to round of error effects. Nevertheless, you still have this speed of info limitation. There is no way how a CG method can solve that system with less than 15 iterations, with less than 16 iterations. With 15, the solution is still dead wrong. There is nothing correct in the solution up to 15 iterations. Only the 16th one is good. And that is interesting because all these methods that would also refer to GMRes and whatever you can cook up in Krylov space methods, they are subject to the speed of information. And what many people are not aware, for example, in incompressible CFD solvers that use CG somehow to do the pressure correction, you have a non-physical speed of sound. That means instead of propagating the incompressibility along the whole domain in each time step, which you should do, you only propagate it as far as you do CG iterations in each time step in a disclosed way. What can help? Well, the obvious answer is multigrid, and so we are eventually getting to the point where I wanted to get to. In 1D, however, multigrid becomes cyclic reduction. That's kind of boring, and so we now have to go 2D. So here is the 2D mesh. We discretize in the standard way, everything normal. Yeah, just a 5-point stencil. I think there's not too much to explain. I think most people have seen that in some way. The matrix looks like this. It's now a pentadiagonal matrix in that structure for 3x3 grid, where I can still plot it. The condition number still goes with the square of the mesh size inverse. So in this case, the number of unknowns. And let's look at this problem. So this is an exact solution of the Poisson equation, sinh type sine. This is the boundary conditions if you just have derivative conditions that you would have. And let's look at what the Gauss-Seidel iteration does. And does the analogous thing what you have seen in 1D, right? The propagation of the information is one grid line away from the boundary per iteration. And therefore, you have the same thing in 2D that we had in 1D. After 100 iterations, you have a solution that looks like this one. In 2D now, it looks nice and smooth. It's a little bit less clear to see. But to see where still the deficit is where if you overlay that with the true solution. And you have the same phenomenon that you're still some between 5 and 10% away of the solution. And the message is now not that you have done 90% of the work and only 10% is left, because before you get the real solution, you have to do 1,000 iterations. So 90% of the work is still to be done when you have arrived at this point. Okay, overlaid with the true solution, you see that 1,000 iterations have been enough. Now, why does multigrid do better here? Because it has this hierarchical structure that you relax on one grid, but then you go to coarser grids. This is an illustration how it goes. So you have this hierarchy of grids. And I would like to illustrate again with a few pictures why this is something that is good. Typical multigrid algorithms do something like 2 steps of smoothing on each level. So let's do that. So this is the boundary condition, 2 steps of smoothing. This is what we have seen. And now comes the recursion that from a coarse grid tries to correct it so that it becomes a true solution. What does that look like? So compute the residual, restrict, relax on the coarser grid. What happens on the coarser grid is this. So this is what happens in the multigrid. You have restricted, you have a residual, you start to relax again. First of all, you should become clear that this is a coarser grid. The finest grid was 32 by 32. This is 16 by 16. And now again, on this grid, the information also spreads by 2 relaxations, by 2 grid lines, only the grid lines are further apart. So the speed with which the information propagates goes quicker. I now kind of jump over all that recursion with many levels potentially in between. And this is what comes up after the recursion, after we've gone through all this, is this one. And note that on the back side, it's 0 because the derivative conditions are corrected with a 0. The derivative conditions are already correct on the finest level. So there's a 0 here on the back, but kind of this hump that's added to the finest grid. And if you do that, it looks like that. This is what comes out of a single V cycle of the multigrid with 2 pre and 1 post relaxation. If you look carefully, you see that it's kind of wobbly there. So it's not a perfect thing, but qualitatively, it is already good, right? Fundamental features of the solution are there even after a single V cycle. And this is a picture how that all fits together. Boundary conditions, 2 steps of relaxation, starting on the coarser grid, computing the residuals, starting relaxation on the coarser grid. Again, from that on, computing residuals on the coarser grid, starting relaxing, propagating the information by 2 more grid lines, going to the next coarser grid. Here we assume, in fact, that we already do terminate the recursion and solve the remaining problem there, and then take this plus this, get this one, where this has to be interpolated to the finer grid. Then take this, interpolate it to the finer grid, add this, get this one, and then finally take this plus this here, interpolate it to the finer grid, get this one, and always one post-smoothing added to that. So this is the mechanics how multigrid works. And here is just a typical convergence plot, while red-black relaxation, so Gauss-Seidel method, would stagnate here and have this very slow convergence Multigrid typically converges, if it's well designed, with a convergence rate of 1 order of magnitude per iteration, so 10 orders of magnitude improvement of the residual after 10 iterations. That is the ideal situation. You can even improve on that by going to the full multigrid, where we combine the grid refinement approach with the V-cycle. And then the message is that if you have a good enough solution already on a finer grid and interpolate to a finer grid, then one V-cycle is enough to get to the level of truncation error. This gives a structure like this. You start, you get down your information on the courses grid, then you start with the exact solver, you interpolate to the next finer grid, you do a very simple V-cycle here, interpolate to the next finer grid, do a simple V-cycle here, interpolate to the finer grid, do a V-cycle, and so on. And in an ideal case, one single V-cycle is enough to get up here the solution which is as good as the discretization permits on that level. And that for simple cases, it can be proven. For more complicated cases, this is more difficult. These were now very simple cases. Now I wanted to demonstrate that we can do some real things, so the kind of stuff that the PhD students here are working on and the collaborators. So we want to use multigrid for earth mantle convection. Earth mantle convection is modeled by a variant of the Stokes equation plus a temperature energy equation. The time dependency is only in the energy equation. The Stokes equation is stationary. That has to do with the physics of the problem, that the dynamics of the evolution driven by the temperature develops on timescales of 10,000, 100,000, millions of years, while the equilibrium in the forces, which is in the Stokes equation, it equilibrates on the timescale of earthquakes, because that is kind of how the pressures and the forces are being balanced in the Earth mantle. So that here if there were a time derivative, it would be acting on the timescale of hours, while this here acts on a timescale of 10,000 years or so. 10,000 years is actually a short time step for the temperature equation. So the hard part is, first of all, this one. So the Stokes equation, it leads to a saddle point system. And one of the ways how to deal with that would be to go to a sure complement formulation. So the saddle point, as it's written here, has a stabilization term because we sometimes use instable discretizations and stabilize. But there are different algorithms to do that and different discretizations that we're trying out. It's a project that has been running for more than 10 years, 12 or 13 years now, in a collaboration between us here in Erlangen and collaborators in Munich, both at TU for the numerics and at LMU for the geophysics. So why do we do that? Because mantle convection is the driving force for plate tectonics, mountain building, earthquakes. And this is how we generate our grid. So the sphere, the spherical shell, the earth mantle is about the layer approximately 3,000 meters under our feet before the molten iron core starts. We start with the icosahedron. We refine once, we refine twice, we refine 3 times, we refine 4 times, we refine 5 times, 6 times, 7 times, 8 times, 9 times, 10 times, 11 times. And then we are down to a mesh. Actually, I think we would need one more level of refinement that has a mesh length of approximately 1 kilometer, which is a typical mesh size that you would want to use to model geology. And since the volume of the whole thing is 10 to the 12 cubic kilometers, it means that your system will immediately grow up to a size of 10 to the 12 mesh cells and the corresponding number of unknowns. And this would then be time dependent. You want to solve the inverse problem and uncertainty quantification. So it could be quite complicated. It's one of the grand challenges if you want to drive it that far. And we have a software called HiTech developed by the PhD students that is driven by this application. It is a more general purpose software product. It can do more things, but one of the driving applications is actually earth mantle. And yeah, let's not talk too much. And so I have this animation that goes back to the dissertation of Niels Kohl, who did his PhD last year, finished his PhD. So the work was, of course, taking longer. And here you can see kind of what this looks like with color coding for the temperatures. The data, the velocity data on the surface comes from the known velocities of the continental plates that are imposed on that. On the molten iron core, there should be a free slip condition. And then you can do all kinds of evaluations, like here the streamlines and the rising and the downwells of the plumes of when colder material sinks down. It's driven by buoyancy forces, as you could see illustrated here. Okay, maybe a quick look here. How is the mesh being generated? So as I said, it is this refined icosahedron. It eventually leads to a tetrahedral mesh as we do it. And then each tetrahedron that comes out of that is refined in that way that was illustrated on the other slide, in a way that has been invented by several people. We typically cite Pi for that, where also a 30-year-old paper, that you cut the edges of the tetrahedron into smaller, in half. Yeah, this is already over it. So the tetrahedron is refined into 8 smaller tetrahedra, and that gives rise to a structured grid. And this is just a sketch of what can be done. The results of a paper that was also published 10 years ago, with the ups and downs of the lithosphere, depending on different assumptions on the viscosity model for the Earth mantle. Okay, here's again a sketch of what is more important in this talk of the tetrahedron. So big tetrahedra, and they are refined in a structured way. And this, of course, also leads to the partitioning, how this is being put on a parallel machine. And the data structures for the interfaces are also driven by the geometry or defined by the geometry to handle the communication. So we have decided rather to go for domain decomposition or, some linear algebra libraries to really go and use Multigrid and implement it for this kind of data structure and this prototype implementation in the best way that we can. So we partition the domain, we parallelize everything on all grids, we try to find the best possible data structures. And then one big decision is that we focus on matrix-free implementations. Why that? Because the largest application, the largest system that will show you in a minute, go up to 10 to the 13 degrees of freedom. 10 to the 13 is a big number. If you store it in double precision, the vector has a size of 80 terabytes. So even on a big machine, you do not store all that many of these vectors. 80 terabytes, maybe on a very big machine nowadays, you can store 10 or so of them, but not much more. And in particular, there's no chance at all to store a matrix. No data structure for a matrix would permit you to set up the matrix and store it. There's simply not enough memory. So we need to do this matrix free. And then we realize that these elliptic problems always require this global communication. So the coarser grids need to be there. There's, a lot of people try to optimize the coarse grids away because they say, yeah, the problem is too small, I cannot parallelize it anymore. Bottom line message to that is, if you optimize the coarse grids away, you have to pay with doing more iterations. It is much better to have a phase in your algorithm where the machine is not completely busy or has a lot of overhead, but there you have to do this data communication, that everything gets the data from everywhere, and tolerate that this gives a slowdown, but it gives you a better algorithm. So what we do is a matrix-free multigrid with an Usawa kind of smoother. It's a monolithic multigrid, not using the block structure at least not directly the block structure of the system. And here you see these 10 to the 13 unknowns. The result that I have here is a relatively old one that was still on Eugene, so a blue gene machine from IBM, which I still like very much because it was very nice for scaling experiments. And here you see a typical scaling experiment. You start with 5 of its nodes. Those people who still know that machine know that the cores were relatively slow. But on 5 nodes, we were able with that matrix-free implementation already to go up to 10 to the 9 degrees of freedom, which 10 years ago was already in itself quite spectacular. But then when we go to almost the full machine of that size, we're up to 10 to the 13. So always kind of multiplying the size by 8, both in terms of number of nodes and number of degrees of freedom. And what you really want to see here is that the compute time stays bounded. And it does, almost. And when you look, why does it not stay perfectly bounded? That is because our coarse grids grows with the number of unknowns. So the coarse grid is not a fixed size, but it grows with the number of processors, basically. And that means that the coarse grid computation will eventually become a bottleneck. Here in the largest computation is at about 12% of the cost. If you were going to still further still bigger, we would have to invent something. But here is the fact that we can do, if really necessary, 10 to the 13 degrees of freedom in compute times of less than 15 minutes. Okay. Here is just a list of references to how saddle point systems can be solved. Now I would like to spend my last 10 minutes on two aspects, and one is code generation. This is something that we have started new, so the current generation of PhD students is very much involved in that. When you try to put everything together and not just a prototype implementation with one application, one finite element discretization, one specific solver, and one architecture that you optimize on, then you have to worry with different discretizations, linear elements, quadratic elements, more complicated elements. You have different domain shapes. Yeah, the spherical shell is already something, but there may be others. You have different kernels for the relaxation, for the grid transfer, for computing residuals, and so on. You have different operators to take care of, the Laplacian, divergence, gradient, combinations of them. You have different ways how to set up your finite element system, whether it's constant coefficient or whether you do some kind of approximations. You have different memory layouts, and you eventually have different platforms where, GPUs, I should say, is something that we keep debating how to best do that. We have several attempts in the past to try it, but we need to try again because the machines are obviously going in that direction. Our general approach, I think, is very well suited because we try to put all that together by automatic code generation. And this is the picture how this is supposed to work. So we have certain optimizations like exploiting symmetry or using vectorization or different looping strategies, so traversals through the grid. Also mathematical optimizations like using different integration rules. And all that leads to a search, what is the best possible optimization for a given part of the algorithm? And this is the technicalities. So liquid is, of course, very useful. We are using the supercomputers here. And to do these experiments. In that optimization, two things come together. There's once the symbolic manipulation, as long as it's more on the mathematical side, when we try to manipulate the mathematical expressions to save and to make them more efficient. But there's also the computer technology from compiler constructions that we set up an abstract syntax tree and that we manipulate the tree as optimizing compilers also do, only that we do that with the target of a special application. So we have much more knowledge of what we can do than a general compiler. So the methods how we do it are similar as you would find in any optimizing compiler, but the knowledge that we have, what can be done, what kind of transformations are correct and potentially useful is one that is tied to the application. So a general purpose compiler can then do them only partially. And here you see one result. So this is just the application of that operator. In terms of linear algebra, it's the application of one of these pentadiagonal matrices or similar matrices, banded matrices that come out of the Laplace operator here in the weak form, here for quadratic element, and with a variable coefficient. And the optimizations, here is the effect of how much the code has been speeding up. So this is the basic code. Then you exploit the symmetry. That leads to a 1.7 speed up. Then you do the vectorization. That leads to another 3.2 speed up. Then you perform that mathematical optimization of changing the integration rule called under integration. That speeds up the code by another factor of 3.8. Then exploit the loop invariance. So whatever is invariant in the loop, you try to pull out. That leads to this other 1.9 speed up. Then you find that the next step you should do is changing the looping strategy, another 1.4, and eventually you tabulate certain values in the loop. And this is illustrated from another view here in a roofline diagram. You start off with a code that in the roofline diagram sits here. Exploiting the symmetry reduces the memory, the flops intensity, less flops for the same work. The vectorization cranks up the number of flops, so you're more moving towards the flops limit. The under integration reduces the number of flops, so you're again moving closer to the bandwidth limit. If you then do the loop invariant, you actually hit the bandwidth limit. So this is a time when you have to do cache optimizations by changing the looping strategy that moves you here, and then the tabulation brings you there. And so the developer who would have to implement all that by hand and try out by hand what is the right order of these optimizations, my students can correct me, but a good student who knows what she or he is doing would easily need half a year to do that manually, maybe more. And so you would only do it once, and then you would never try to touch it again, because it's not always pleasant work. Now that it's optimized, you can always play with it. Right? And then for a different operator and a different configuration, a different mesh, it might actually be a different optimization. Since it's optimized, you can always regenerate it. I would like to bring up one more notion. Textbook multigrid efficiency. So one of the promoters of Brandt from the 1980s, of multigrid, Brandt from the 1980s, has this program for himself and then maybe also for others. He claims that every in the core elliptic PDE should be solvable with a cost that is equal or less than 10 multiplications of the operator itself. This is a very ambitious goal. And what we try to do is to show that this is possible. So this is much more than just showing that you have asymptotic optimality, because it also dictates what kind of a constant you should have. That constant should be less than 10, and the work unit is one matrix vector multiplication. This is, again, work by Niels, which I think is a very nice view on that. Actually, maybe Niels is even online. I haven't checked. This looks like a typical convergence diagram, right? So you do more iterations down here, and the accuracy improves. These are two diagrams. The one diagram is the second order discretization with linear elements, and the red is this. So this is linear elements, and this is quadratic elements. Quadratic elements should, in the L2 norm, have cubic convergence. But this is not a standard diagram, because each of the dots marks the point where we have used the best possible algorithm. A work unit here is really just one matrix vector multiplication. So if you are permitting yourself just to do one matrix vector multiplication, there's really nothing you can do to solve the system. But interestingly enough, if you just do two matrix vector multiplications, you can already have an algorithm that gives you reasonable accuracy. How is that possible? Well, here is a little bit of a trick involved. If you can design your multigrid algorithm, for example, you can solve on the Lex coarser grid quite accurately and then interpolate to the finer grid, and there basically just do one additional Gauss-Seidel smoothing. Because on the coarser grid, it's much cheaper, right? And this is, of course, reflected here. So these here are solutions which are coming out of something like that. You solve the coarser grid problem fairly accurately and interpolate it to the finer grid, and there you basically leave it alone. That is already not so bad in terms of accuracy. And in particular, it's interesting that the P2 solution is already more accurate than the P1 solution will eventually give you in the asymptotic limit. So in principle, it says, if you are work limited, better solve with a higher order finite elements on the coarser grid than solving with low order finite elements on the finer grid. That's maybe not the answer that you wanted to have. But still, you see that with something like 6 work units, with the P1 discretization, you have exploited more or less what it can asymptotically give you. It does not get much better after 6 work units. And for the somewhat more ambitious discretization with 2 elements, maybe 8 or at most 10 work units are also enough. So this claim of textbook multigrid efficiency, at least for here, and this is already Stokes' equation, you can find algorithms that do that. Of course, this depends also what kind of smoothness you have in your model problem. For different problems, this might look different. So with that, it's time to come back to this question. Now, the very simple one, Poisson's equation in the unit square. How many flops do you need to solve it to discretization error level? We have to dig very deep into the literature to find that. 82 is a paper that I want to cite. Here's a copy out of that. You can see that it's quite dusty or just from the typesetting. But if you wipe the dust off, it's still good, healthy, and solid numerics. Very carefully worked out convergence rates, counting the number of flops up to the decimal places, working that all out. Optimizing, like knowing that when you do red-black, you have 0 residuals at some places, you can cleverly use that. All these tricks are in there. And then you find that you can do a single V cycle with 20 flops per unknown. And if you do that combined with full multigrid, you get this full multigrid algorithm that should solve a problem up to discretization error accuracy with 30 flops per unknown. 30. It's very little. Actually, 30 flops is in cost less than, say, evaluating 2 trig functions. So even if your solution is given to you as a product of 2 sine functions, evaluating this analytical formula is more expensive than solving it numerically from that perspective. So it's fairly surprising. And if we look at that, so the kind of disappointing part comes now when you try to convert what that means. Say, even a petaflop computer, less performance than we have here sitting in the computing center, and you wanted to solve a system with 10 to the 9 unknowns, and many people here would still think that 10 to the 9 unknowns is a quite large system, you should be able to solve the Poisson equation in something like 30 microseconds. And then everybody who tries that now starts to laugh, because we all know that this is completely unrealistic, right? So we would be happy to get it in seconds, but definitely not in microseconds. Maybe fractions of a second, maybe tens or hundreds of milliseconds. So the state of the art is that in computational practice, we miss this by several orders of magnitude. And that this simple computation is, of course, unrealistic, I will immediately believe. And if you say to me, oh, our computer architectures are such that we cannot get more than, for PDE and sparse matrices, we cannot get more than 10% or maybe 5% of the peak performance, I will immediately believe that. But while we are losing 2 or 3 orders of magnitude in performance, I'm not sure that this is justified. So there's a question, where does this gap between theory and practice come from? We obviously need to look more carefully. And of course, our discretizations are more complex. We have more complicated systems and discretizations and boundary conditions and all that. But still, I think the width of the gap is not justified by all that. And with that, I would like to conclude. So multigrid is scalable. That's good. We have been working on that for the better part of the last 25 years. We have been reaching 10 to the 13 degrees of freedom. That new software is now much more flexible, sustainable, can also work with better discretizations. But we still see an efficiency that seems to be suboptimal when compared with the plain old-fashioned algorithms and software of 40 years ago. And here are some links, and that's also an old animation that comes from several years ago. With that, thanks for your attention, and I will be happy to take up any questions that may be there. So when in the abstract I said, what is efficiency? I'm after 30 years of working with that, I still don't know. And I'm not sure that when I see it, it's really efficiency. So it's more unclear to me than ever.
All right. Thanks a lot for this very enlightening talk. Are there any questions here in the room? Just speak up, or in the Zoom, put it in the chat, or unmute yourself. We can hear you.
I've seen it. So personally, I'm more in the discrete simulation field. I'm interested in continuous simulation. I've seen a method that does a, what do you call it, non-homogeneous relaxation, something like this. So for fluid dynamics, so I guess you look at the speed of fluid on the gradients, etc., and adaptively to go to a coarser grid or a non-so-coarse grid, depending on your gradients. Do you have experience with methods like this?
Yeah. So of course, this is in many cases is essentially, say, in our fluid dynamics code Valvula that I did not touch at all here. We do have a setup where we can refine the grid where the physics require that. Typically, when you have the flow around an obstacle, you try to resolve the obstacle with a finer grid than the far field. And that can be done statically, meaning that a priori you say, here is my landing gear, and that landing gear is as it is. So I design the mesh for it, and then I do my simulations. Or it can be that even more challenging, of course, that you dynamically adapt that as the flow field evolves, you try to refine the grid. We have an example, Philip is sitting there, he's working on rotors and then try to kind of move the mesh or refine the mesh with the rotating object in the flow field. So refine where the rotor blades are and de-refine where they not are, which turns out in parallel not to be so easy, right? So very easily you have something that does that, but whatever it brings you in terms of saving mesh points, it loses in efficiency. So it's kind of tricky to get that. But eventually, of course, we need that. We should try to develop that, and it is possible. And I don't know whether Benjamin is here. We of course also try to do something similar to that with the finite element meshes of high-tech, where there's also a compromise, because the fundamental idea is that you have an unstructured grid, but on top of that, you use a structured refinement. And the philosophy why we do it in that way is because we want to exploit the structuredness of these blocks, we call them macros, to gain efficiency, because only then can we easily design different traversal routes if there's a structuredness that tells us how we can reconfigure our loops to get better performance. In an unstructured mesh, this would be not so easy. But on the other hand, it restricts what we can do when we have to refine the mesh, right? So we then have to go detours to do that. So it comes at a price.
I would like to thank you for your presentation. And my question is, for example, we consider a Navier-Stokes equation or a diffusion equation, what is the super resolution, for example, by comparing these methods with the PEN.
What is PEN? I may have not
understood. Physics neural network.
Okay, neural networks. So I would say using neural networks for PDEs and in particular fluid dynamics is wide open. There are some very interesting papers showing very good success. On the other hand, one has to be really quite careful. So one of the people with whom we have been working and then publications were, for example, using the neural network in fluid dynamics to compute the pressure correction with eventually a Poisson equation. The pressure Poisson equation is in principle a Poisson equation. And they used neural networks on that. It's now 2 or 3 years old. In that field, 2 or 3 years is already quite old, but usually it is not so old. And our result was that we computed the number of flops that they need to do that on the order, if I have the number right on top of my head, on the order of 100,000 per unknown. So compared to the 30 that I showed here, this is completely ridiculous. But that is this one particular thing. And if you use neural networks, we have also other PhD students who work on that. There seems to be a niche in terms of using neural networks for surrogate models. So if you need many solutions with modest accuracy, then it is, of course, related to all these questions of reduced order modeling that from the mathematics community have been studied for the better part of the past 15 years or so. And these would be kind of the competitors that you have to compare the neural networks to. But, you know, this is what I know, and this is a very limited knowledge because the number of publications in that field is growing so quickly that I'm feeling overwhelmed and can only read a subset of them. So if there's a breakthrough paper, I may simply not know it.
Thank you. Thank you.
A follow-up question on the surrogate models. Do you have any information about the architectures typically employed for those models? Are they recurrent? I guess they have to have some memory, or like the inner working of the network architecture.
Again, I do not have a complete overview. What we have been using with some success are UNet models. And if you look at the structure of multigrid, using a UNet that uses kind of layers that are smaller in between is of kind of, it's natural for us because this is close to our way of thinking in multigrid anyway. And these seem to have some advantages. But again, I don't think my colleague Harald or anybody working with him on neural networks is here and could comment on that. What kind of neural networks were the most successful? I'm actually not quite sure.
There's a question from the chat. Is multigrid also applicable in case of high Reynolds numbers with fully turbulent flows, where it's hard to reduce the error on coarse grids?
The statement with this 30 flops per unknown, if you're for the moment taking 2D, would be independent of what the solution looks like. It is for a very rough solution that you might have with turbulence versus as well as for a very smooth solution. So it is for the whole, from a linear algebra perspective, for the whole vector space. It's independent of what the solution looks like. And therefore, I would imagine that it works for all the Reynolds numbers. But I know that from the CFD community, there are studies how this depends on the Reynolds number. I have seen some of these. And if the solver is more CG related, that might really play a role. What the style or what the shape of the solution is, because Krylov space methods will typically depend on whether the solution lives in a smaller dimensional subspace, then they are better than if it's kind of distributed over the whole spectrum of spaces of space, which might be the case for Reynolds numbers. But that is something that I would expect for a Krylov method, not for multigrid.
I have a question. You mentioned the 30 flops per unknown. And of course, in computing, it's not so much how much work I have to do, but what's the limiting resource that I have to rely on? And my question would be, if 30 is the number of flops you need to solve the problem, what is the number of bytes you need to solve the problem to go along with these 30 flops? Because the data has to be somewhere.
Okay. The first and simple answer is, let's first talk about data transport. Because I think we too would agree that for a sparse matrix, actually transporting the data is a more limiting resource than computing the flops on the sparse matrix. And there, the simple answer is if there are only 30 flops to do, there are also not more than 30 operands, and so there's not 30 times 8 bytes times that, and you could kind of from the bandwidth compute an upper bound of what you should be seeing. And then by looking more carefully, in principle, you have to take the result vector and pump it through the memory hierarchy or whatever it is 3 or 4 times, not more. And so that's would be one of the limits. The other question is a much more tricky one, because this optimality of the multigrid, the 30n, of course, depends on the floating point accuracy to be enough to represent your solution. And there's, of course, the question when you're up at 10 to the 12 unknowns, whether this is still enough to represent your solution. Actually, I've been promising to say something about that, because we have people who look at mixed precision and everything. And so if you especially work with reduced precision, this is very quickly not enough if you work in a conventional way. So that's the answer. Then, however, this gives rise to another idea. And the person who would know everything about that was sitting right behind you and had to leave already, because he has a paper which will be presented in the Copper Mountain Conference 2 months in the US. And what he has developed together with 2 co-authors, McCormick and Tamsdorf, is a multigrid variant where on each grid you do not store a full floating point number with whatever precision, but you store on the finer grids only so offsets from the next Corsa level. So in principle, that means you could get away, if that works and is universal enough, by not storing floating point numbers on each level, which would have the danger when you go finer and finer, need more accuracy, you need more and more bytes, more and more bits to represent that accuracy. You store on each level only a finite number of bytes, and you get your accuracy by using the Corsa grids to define your solution. A finite number, and so if you have 10 levels, your solution at any given point would be given by summing 10 fixed bit numbers in the right way to get it. And that's easily said again, right? But designing the algorithms so that you don't have an overhead that kills your efficiency at another point is not easy. And I'm still not completely convinced that it's universal enough, what they have done. Because even when I was a postdoc, we had master theses that were trying something equivalent, so 40 years ago or something. And we was more or less failed on doing it. So it was not so easy. At least at that time we couldn't do it. But now Daniel is maybe more clever and has been able to do it.
Hi, Uli. Thanks for the talk. Recently, I've been talking to people who build very large machines, and you're obviously a user of very large machines. They all seem to be convinced that we're never going to get away from GPUs again. So I got a bit depressed that you said you haven't been able to do GPUs. So what's the gap in terms of, for instance, roofline performance? Like, how far did you get?
So with an older version of this high-tech software, we had one attempt to port that to GPUs approximately 10 years ago. And we essentially failed to do that. But these were the GPUs of 10 years ago. And the problem for our data structures is that we have these tetrahedral grids. That means a grid traversal will not have a nested loop with the same loop length, but the loop length will constantly vary. And that was a killer for the GPUs 10 years ago. Basically, the only way how to get that done was kind of going in direction, which was more or less equivalent of setting up the matrix and using a sparse matrix data structure. And so whatever performance a GPU was possible or might have given you, a good deal of that was eaten up by having to use more complicated algorithms. So we gave up on that at that time. Now the GPUs are different, and the chances to do that are there. I do think it is possible now. The question is when asymptotically it will bring a benefit. You know, these structured blocks have to be big enough for the GPUs to have a real benefit. And so that needs to be explored. The other thing is, since we have so highly optimized kernels for CPUs, right? If we had lousy implementations on CPUs, then using a GPU would be nice and easy to get a 10-fold speed up. But as always, if you're already on a high level, it is hard to find a competitor that beats it. And all this effort of using GPUs, then to find that in some examples you have a 2-fold speed up, and in others it's only 10%, and there are a few more where it's no speed up at all. And you know, sacrificing a PhD student and 3 years for doing that is questionable. So we need to think about that, how we approach that.
Well, I'm also very happy.
But you're right.
I'm also very happy to have a good CPU code that proves that CPUs are still useful.
Yeah, but they are taking the machines away from us. And say we are in EU projects where basically the condition is that you have the condition is not that you have a fast code that works fast on the given set of machines, one of the given machines, but the condition is, do you have a GPU version? And if not, try to do a GPU port. And for reasons that I don't like, then how much speed up that you really get and how really well you exploit the GPU architecture is then only of secondary importance. Because there are a lot of GPU ports already out there, which are, only so-so. A really good GPU port that really exploits the GPU in terms of being in the roofline diagram at a good spot is not so easy.
My final question, where does this number of 10 come from for the textbook efficiency? Was it just a hunch? Or is it rooted in some mathematical analysis?
I think that Achim Brandt knew that the Poisson, this constant, would be something around 3. And he said, okay, let's give a little bit of slack and take a natural number for more complicated equations. I do think if you're reaching it with 12 or something, you know, variable coefficients, Stokes, whatever, non-symmetric, Navier-Stokes, then this is still a great result then. And I would not object to calling it textbook efficiency, but somewhere on that order, not too much higher.